Hi everyone. There's a little more on the first case, that is the underdamped oscillations. That is light damping. So we got the expression for the displacement as x is equal to a raised to minus gamma by 2 into t cos omega 1 t plus phi, and this indicates that there is an exponential decreasing amplitude, and there is also no oscillatory time. You can draw the time displacement curve of a damping oscillation, and it will be like this. Here the amplitude of the oscillator decreases with time. Now, strictly speaking, the oscillations of a damped oscillator will not be periodic, since the amplitude is continuously decreasing with time. So, and however, when the damping is very small, that is when gamma is less than 0, that is the underdamped case, the motion is almost periodic. We take it as almost periodic, and the angular frequency will be omega 1. Remember how we have done the solution, that is how we have substituted omega 1 in the earlier equation. So omega 1 will be root of omega 0 square minus gamma square by 4, and the corresponding period of oscillation will be 2 pi by omega 1. 2 pi by omega 1, that is 2 pi divided by root of omega 0 square minus gamma square by 4. T is equal to 2 pi by omega 1, that is equal to 2 pi by omega 0 minus gamma square by 4. Okay, hope you have understood with the first case. Now we will move to the second case, that is the overdamped or heavily damped oscillations, or heavily damped case. So here heavily damped, that has the term, and the term tells you the gamma, the damping constant, is much greater than omega 0, that is the natural frequency of the harmonic oscillator. Now we can say that since gamma is greater than omega 0, then the root of gamma square by 4 minus omega 0 square will be a real quantity. So we have the equation, for the solution for the differential equation that we got earlier is x is equal to e raised to minus gamma by 2 into t c1 exponential root of gamma square by 4 minus omega 0 square into t plus c2 exponential minus of root of gamma square by 4 minus omega square into t. Here this term will be a positive quantity because gamma is greater than 1. Just remember that in the last case, that is underdamped case, gamma was less than omega 0, and in that case we took a minus sign outside in order to make the root a positive quantity. Here there is no such problems arise, since gamma is greater than omega 0, so there will be, this value will be definitely a positive quantity. So you can substitute root of gamma square by 4 minus omega 0 square as beta. Now the equation simplifies to x is equal to e raised to minus gamma by 2 into t c1 exponential beta t plus c2 exponential minus beta t. And when you see this equation, gamma by 2 is greater than omega 0 and gamma by 2 is greater than beta. This condition arises from this. See, when gamma by 2 is greater than omega 0, this will be a positive quantity. So, positive quantity, and when gamma by 2 is greater than beta. So the difference beta will be less than the gamma by 2. So here you can see that both the terms in the equation decreases exponentially with time. See, as the time increases, see when t goes to infinity, what happens? When t goes to infinity, e raised to minus infinity will come for the this term. So e raised to minus infinity will be go to 0, and the next term also this will be e raised to minus gamma by 2 into t, and e raised to minus beta t. This product will also go to 0 as t tends to infinity when t increases. T increases. Okay. The result is that the system will not perform an oscillatory motion. And such a system is, when such a system is disturbed, it will return to equilibrium disposition very, very slowly. The motion is called aperiodic because it takes long time to return to the equilibrium position. We just remember what is the equilibrium position when for such a oscillator, when it is disturbed, it will come back to the equilibrium very, very slow. And the application of this is in deadbeat or galvanometer.